Alright, today we're going to be doing problem number 1 of homework number 8. Now, problem number 1 reads as, given this variable x in terms of t is a WSS or wide sense stationary process, in which case we have the expected value of our x in terms of t is equal to some sort of constant value, n, and that our autocorrelation of our x variable is equal to, between these two time points, is equal to basically the difference of those time points, which is basically a difference of, let's say, t1 minus t2. Alright, so this is equal to that. We have as given. Finally, we have another variable, which we call y, which is also in terms of t, which we define as basically the derivative of our x variable. Alright? Problem number 1 asks us to do 3 things. Find the expected value in terms of our y variable, find the expected value of the product of our two, of x and y, and finally it asks us to prove whether we have, if the terms x and y are uncorrelated or orthogonal. So let's begin simply. So if we're going to do the expected value of y, basically we start with this term. We substitute in right here, knowing that y is basically the derivative of x, right here. Now, because it's the derivative of x, we can actually bring out the derivative term from this equation. Like, the order is interchangeable, so we actually bring out the derivative over here, so the d over dt, and we can actually look at this as the expected value of x in terms of t. Alright? Now we know from up here that that's a constant, n. Right? So the derivative of a constant is going to be 0. So our answer for the expected value of y in terms of t is 0. Now, proceeding to part B, we're looking for the expected value of the product of the two variables. Now, we can do this a couple ways. I did this in 2 ways, actually. They're both interchangeable. It just depends on how you want to start it. Alright, let's start with this one, because it just flows a little better, I guess. If we actually start with our term, what we're looking to get, alright, again, we substitute in for y, our definition, right here. So we get this term, alright. Now, this term right here, we can bring out the d dt out, and actually, this ends up being, if we bring this out, ends up being 1/2 times x squared in terms of t. So we can actually bring out the constant term, the derivative, the d over dt term, and we rewrite this. Now, if we look at this, this term is just basically the definition of our autocorrelation at one time point t. Alright? Which we can rewrite right here. Now, one time point t, because of how we actually we defined it in terms of the difference. So if it's a single point, say, t minus t, it just becomes t minus t. So r of x in terms of tau, it's basically we're writing r of 0, okay? And in that case, r of 0 is 0. So basically, our derivative of 0 is 0. Alternatively, we could have started with our autocorrelation term and played it out by definition, seeing how using the derivative right here and we can see how this equates because we're working with wide sense stationary. And we could actually play this out, seeing how this is equivalent to basically the square of the x term. And if we continue to do it like this, right here, we actually take the derivative, which basically is 2 times the expected value of x times the exponential. And since this right here is equal to our y term, we substitute in. So basically, this term right here is what we're looking for right here. So basically what we have is 2 times the expected value of the product of x and y is going to be equal to 0. So if we work it out, what we end up with, the 2 cancels out, and this ends up being 0. So our final term, however you want to work it out, is going to be 0. Finally, we're asked in part C and D, which I combined right here. C is basically ask us if x and y are uncorrelated, and D asks us if they're orthogonal. Now, based on what we worked out up here, here we basically have the given that this term is equal to 0. This term right here we got from part A is equal to 0. We can see that if we do the expected value, we multiply the expected values of each of our variables. I mean, this by definition is equal to the n, is equal to, this is going to be 0. So if we combine all this information right here, what we're seeing is that this, which is equal to 0, is also going to be equal to this. All right, all of this equal to 0. Since basically the expected value of our product is equal to the product of our individual expected values for the two variables, we prove that we have these two variables are uncorrelated. Furthermore, because this term right here is equal to 0, that abides by the definition of being orthogonal. Hence, what we show is that x and y are both uncorrelated and orthogonal. Hence ends our proof for problem number 1 of homework 8.